Hi, I am Sumant Kumar Kambalimat. I welcome you all to my today's presentation. So the topic is evolution of plant or crop phenotyping. So this is very interesting topic. I think everyone will enjoy this topic. So before initiating the discussion on the topic, we'll know how the relevance of the topic. So we know the current challenges faced by India, like the biggest challenge is increase in population. We see at the current rate, in the picture you can see, at the current rate India will surpass China in few more years. So we will become number one in terms of population in the world. The other second important challenge is shrinking land area. You can see in the picture how in 1976 to 77 the land holding was 2 hectares. So after that it has decreased to 1 hectares. So this is the biggest because of the problem of rapid urbanization, where agriculture lands are converted to residential areas, which obviously are becoming non-cultivable. So the other challenge is, the next challenge is uh, reverse flow is shrinking. You can see in the graph where y-axis is listed with different rivers and x-axis with the water scarcity scale, which is represented from 0 to 12. Uh, for example, you can see river Kaveri is facing severe water stress in terms of flow for several months. Similarly, for the other rivers also, you can see that. So this will affect the farmers and agriculture, which directly hits their income and affects their dependency on this profession. So these are the important current challenges which India is facing now. Okay. But till now, agriculture science did exceptionally well, in progress from famine to self-sufficiency with the help of traditional breeding method. So we need to especially thank breeders and other plant researchers for this. But given the challenges, the yield of a crop need to be improved from 2% from current 1%. But the problem is, yield, you can see from the picture, yield seems to have attained plateaued and stagnated. Uh, you can see the rate of yield increase is stagnated for crops like especially wheat and rice, which we call all as a staple crops. So our major focus is to improve the yield under water limited or resource limited condition. So our answer here is genetic enhancement of desirable traits. How we need to attain this? By genetic enhancement of desired traits or characters which are contributing for the yield. So many physiologists and breeders have dissected the yield into component traits which further regulate the yield. Like in the picture you can see, which is taken from the Reynolds, uh, the breeder, physiological breeder at CIMIT, where he explains the outcome of his experiment, where biomass and harvest index are traits regulating a yield. So biomass is further regulated by how a plant intercept a given light with stay green traits, and after intercepting, how it uses light efficiently. So this is regarding with the biomass. So similarly, harvest index is regulated by grain size traits. So like this, we need to identify the traits controlling yield. So after recognizing the trait regulating yield, we need to capture this variation of a trait through tools like phenotyping and genotyping, which is very important. So we know that in the past 20 years, significant advances were made towards characterization of plant genome. We can see in the picture how the evolution of genotyping has happened, uh, starting from a manual gel method to present generation sequencing methods. So this is happening with the important thing is decreased cost. So this molecular tools have helped breeders to find genomic variation regulating a trait. So now the only thing is remained is phenotyping. So this has become a bottleneck for us. So from the table you can see how traits are phenotyped with conventional methods. So here many methods involved measuring the trait by contact and destructive methods. So this is a kind of phenotyping with destructive method. You know, with will affect the physiology and phenology of a plant. So what is the alternative from this? So we should continue with this destructive kind of method of phenotyping, or we have evolved to a new methods of phenotyping. Let's see. So if you look phenotyping in the breeders program, the main requirements are phenotyping should be how breeders look into the phenotyping. It should be non-destructive. He wants phenotyping to be done for large number of plants at a stretch, and he wants phenotyping should be done with a good resolution, and most important is lower cost with less resources. So for all this, the high throughput plant phenotyping will become the answer for this. So if we look into the breeding equation, genetic gain is equals to selection intensity times selection accuracy and times the genetic variation divided by time taken. So high throughput plant phenotyping directly contributes to, you can see here, high throughput plant phenotyping directly contributes to selection intensity by covering large plant population for selecting a target trait. So it naturally becomes high throughput. So the other thing here is high throughput plant phenotyping increases resolution, accuracy and precision of data obtained. So indirectly it will also capture the spatial variation that will be added value for the trait capturing. So high throughput plant phenotyping is directly uh, involved in identifying genetic variation or trait variation. Thus, this will with all this high throughput plant phenotyping will enhance the genetic gain, which is required by the breeders. So if you see the acceptability of high throughput plant phenotyping technology, it is gaining momentum with several institutes are investing on this. In India, especially ICR institutions like IRI has facility with Nanaji Deshmukh facility, with other institutions like Department of Crop Physiology has a facility, and established by Dr. Uday Kumar, uh, and industries like Hyphen, Lemnatech are involved in the high throughput plant phenotyping facilities. So the other challenge is the acceptability of high throughput phenotyping is, you know, here you can see it shows the reflection of high throughput acceptability of high throughput plant phenotyping in terms of publications. Directly, if you have more facilities, the chance of publication will be more. So if you see, India is far behind, and I hope it will pick up the pace. So now let us dive deeper into the this high throughput plant phenotyping. So you see, it can be classified as uh, two methods: plant to sensor and sensor to plant methods. Especially in plant to sensor method, the plants move towards sensor. The example here is conveyor belt phenotyping facility, which you find in Nanaji Deshmukh facility in IRI. So in sensor to plant method, the sensor moves towards plants, and most of the platforms are this type. Uh, if you see different facilities across the world, so these platforms, you can see more number of platforms are this type. So the major component of high throughput plant phenotyping are sensors and the mounting platforms. So what is sensor? Sensor is the one which converts physical information as an input to biological information as an output. For example, you can see here there are two plants. Here one is water stressed and the other is non-stressed plant. The sensor captures temperature of a plant as a physical information and converts into biological information with the help of mathematical models and the formulas. This is how sensor works. So based on the source of light, sensors are classified as active and passive sensors. So active sensors have their own source of light and it will capture the reflected light, while on the other hand, passive sensors will not have its own source of light, but will capture the reflected light originated from the ambient light. So various sensors are available now in the market which can capture the data in various spectrum range. So we have a RGB camera which can operate between 400 to 700 nanometer range. There are other multispectral camera fluorescence image based systems which can operate between 900 to 1700 nanometers. Hyperspectral camera operate in the range between 350 to 2500 nanometer, while thermal imaging cameras operate in the range between 7 to 14 micrometer range. So we can see hyperspectral imaging covers long range between 350 to 250 nanometer, which can capture chlorophyll data, water content, protein and other parameters. So we will see briefly how visible digital camera work in a principle. So just we'll see how it will work in a principle. Visible camera is also known as RGB camera, as it captures reflected light from red, green and blue bands of visible spectrum. For example, if we need to capture an image of a leaf, we need a light source of a white light here. So when the white light falls on the leaf, it reflects the light and the reflected light will be captured by RGB or visible camera. So three wavelengths of light is captured here. So that is red, green and blue. So then the image can be redrawn through software. Here the important thing is the traits which are captured. Most of the traits are captured like which having the length, morphology, counts, colors and architecture. The other thing is the advantage of this camera is its low cost, high resolution and user friendly operation, and it is extremely lightweight, so you can use these cameras for your experiments. So there are other cameras called non-visible spectral cameras. One is a multispectral camera, the other is hyperspectral camera. So multispectral cameras are mostly having 5 to 6 bands in VNIR region, that is visible near infrared region. So in other camera called hyperspectral camera, which consists of many bands between 350 to 2500 nanometer range. Now we'll consider another example where we can see how the multispectral camera works and operates in a principle. So unlike we saw on other slide, where white light source of light was used. Here in multispectral camera, we have light with different wavelength. So the light is reflected from the leaf, and reflected light will be captured by multispectral camera. So you will get a grayscale image of different wavelengths and intensities. So these can capture um, dimensions, especially these multispectral cameras can capture the traits like which are having dimension, morphology, color, and indices, which tells the which describes the physiological activity of a plant. Sorry. uh, Now we will see how we look into how indices can be captured from a camera. uh, we have light source and a leaf material. Here we have a red light source, and once the leaf absorbs certain light and reflects certain same light, so the image will be captured by a camera. So uh, so here the image you see depends on how much the chlorophyll absorbs the red light. So here chlorophyll absorbs more of red light and reflects less light. So that's the reason you can see the image appears will be darker. So again, the source of light is here, it is changed to far red source. Earlier it was red light, now it has changed to far red source. So here in this light, the chlorophyll absorbs very less here, and it reflects more. So that's the reason it appears bright. So hence the normalized difference vegetative indices is calculated from the differences in the data captured from the red light and far red light with the this formula. So this will reflect the plant health status of a crop. So till now we have seen the principle, operating principle. Uh, Now the sensors, if you see, it can be classified. The majority of the sensors used in high throughput plant phenotyping are imaging sensors. We have five imaging sensors. Prominent five imaging sensors are five, like visible imaging sensor, thermal imaging sensors, fluorescence imaging sensors, and spectral imaging sensors, and lidar. So with this visible imaging sensors, you can capture morphological and architectural traits. With thermal imaging sensor, we can record canopy temperature, which reflects the stomatal conductance and root traits. So with the fluorescence imaging sensors, we can capture the photosynthesis and stress status of a plant. The other imaging sensors, which if you see, there comes a spectroscopic imaging sensors, like for example hyperspectral sensors and multispectral sensors, which gives a water status and health status of a plant canopy. There will be multiple bands. You can capture many data points, and you can assess the health status of a plant or canopy. The other important fifth important sensor is lidar, which will give you to estimate the biomass and plant height, volume of a plant or crop. So this how the lidar will be used for capturing these kind of a traits. So till now we have seen sensor component of high throughput plant phenotyping, right? So now let us turn to another component of high throughput plant phenotyping. So these are ground based platforms and aerial based platforms. So one, you have sensors, and now you need to attach these sensors to the mounting platforms. So these are ground based platforms like phenopoles, phenomobiles, stationary platforms. So the phenopoles, if you see, it can capture the data. If you see the scale of capturing of the data, it captures from a plant or plot scale. The scale will be from the plant or plot. So the other, if you go for the other platforms like phenomobiles or autonomous vehicles, which can capture the data um, with the scale of field, plot, and plant data. And these other gantry systems like stationary platform, which we say here, the imaging systems will capture the data while moving over the field and crops. Coming to the other excuse so coming to the other aerial platforms, we need to capture the data. If you want to capture the data of entire field in a single snapshot, we can use these aerial based platforms. And the disadvantage of the system is payload and resolution. When we are capturing field from the top view, because aerial platforms will capture the view from top, so there is the resolution sometimes will become a problem. Now we will discuss how these will be a pro and cons for aerial and ground based platforms. Ground based high throughput plant phenotyping opens more possibilities of a sensor viewing angles in comparison to aerial counterpart. For short crops, the majority of these high throughput plant phenotyping systems employ a top view imaging strategy. So top view imaging is efficient and effective in quantifying plot level traits such as, for example, NDVI, LAI, and leaf temperature. So however, for small, some tall crops, imaging from a side view angle can capture information that cannot be accessed from the top view. So for example, imaging cereal crops from side can reveal plant architectural traits such as plant height, biomass, leaf angle, etc. So which we can't cover from the top view angle. So that's where some aerial ground based platforms have an edge compared to the aerial based platforms. So now, so these are the various platforms which I was describing till now. You can see conveyor belt platforms, autonomous vehicle platform, and field gantry stationary platform. And these are box phenotyping, where we can use the box and sensors, light systems, just covering the entire plant in a field. And this is spider system. This is another kind of a gantry kind of a system. So these are the just few examples of a phenotyping platforms. So after getting the huge data from now we got the huge data from the high throughput plant phenotyping through sensors with the help of mounting platforms. So after getting this huge data, we need to analyze this. So there are various open source analysis platforms where you can directly use them to generate the results. I have mentioned here one among many open source platforms called as quantitative plant, where you can use this for data analysis or any purpose. So finally, you can see in this picture, you have different sensors which will capture the data, and the data is processed. Data is processed here. So, and it is run in the models, and it will be validated, and finally you will get the final output, whether you can use for the prediction or anything. This is how this from sensors to models, include with the help of high throughput plant prototyping, it will work. So in conclusion, people used to phenotype manually. Even now also they do that, but parallelly we got handheld sensors for phenotyping. Now people are thinking of especially non-invasive, because uh, people are going for non-invasive and non-contact type of phenotyping. For this reason, various plant phenotyping platforms are evolved. So, you see, if you see from domestication, 10,000 years back, people have selected traits based on the phenotyping only. So, phenotyping will always remain king in terms of plant selection. So, uh, without phenotyping, can't do anything, and it has remained important selection criteria. So, so this is about phenotyping and its evolution. Okay, thank you.